Okay, this is Unit 12 of Chemistry. We're going to be looking at solutions in this unit. This first part is going to cover water and its properties. Your objective is C10A. You're going to describe the unique role of water in chemical and biological systems. We're going to be talking first of all about water in the liquid state. When you think water, this is probably what you think. You of course already know that water is H2O. In a deeper sense, what that means is that hydrogen is bonded covalently to oxygen. Because of their placement on the periodic table, you can tell that oxygen and hydrogen have a very large difference in electronegativity. Oxygen is a much larger atom, it has a more attractive nucleus, and so it pulls much harder on the electrons that are shared, and as a result, hydrogen doesn't have the electrons as close to the hydrogen end of the molecule as oxygen does. The result of that is that water is what we call a polar molecule. When you think polar here, don't think about Antarctica or white bears. Think poles like the poles of a magnet. You know, if you have a magnet that's got a north pole and a south pole, if you try and put those two north poles together, they don't attract each other, they repel, but if you flip one around and attract the north to the south, they will end up attracting each other. Same thing with water molecules, except instead of dealing with magnetic attraction, you're dealing with electrical attraction. You can see in this diagram right here, this shows the charge on a water molecule down here at the oxygen end, where the electrons spend most of their time. That's going to result in a negative charge at that end of the molecule. Up here at the hydrogen end, there's an overall positive charge. Now this results in some pretty strange things. First of all, in water you get a lot of what's called hydrogen bonding. This isn't a conventional bond like an ionic bond or a covalent bond. This is really more of a weak attraction between the hydrogen end of one water molecule and the oxygen end of another water molecule. And by itself, that is not a very strong bond. But if you consider the fact that anytime you've got two water molecules, you more likely have 2 billion water molecules, and you multiply that force out billions of times, then it becomes really quite strong. Think of it kind of like in a Velcro strip. If you just take one little hook and one little loop in Velcro and join them together, it's relatively easy to break. But if you take a large strip of Velcro, hooks and loops, put them together, that force is multiplied out, so the overall force is really fairly strong. And it's that hydrogen bonding and that unequal sharing of electrons between the oxygen and the hydrogen that gives water all of its unusual properties. One of the things that hydrogen bonding causes is surface tension. Surface tension, if you have a container of water, at the surface of that water, those water molecules are hydrogen bonded together. They're grabbing onto each other very tightly. And that force is so strong that if something is sitting on top of that water, say this pond skimmer right here, they can actually walk on the surface of the water without breaking that surface tension. It would be much like you or I walking on a trampoline. We bend it a little bit, but we're not going to step through it. You can play around with surface tension quite a bit. Take a paper clip, turn it on its side, and use a fork to lower it very slowly into a bowl of water. And if you do it just right, that paper clip will actually float on the surface of the water, so long as you don't break that surface tension. You can also play around with the surface tension of water if you take a penny and you take a medicine dropper and you drop drops of water onto the head of that penny. You can actually get more than 100 drops of water onto the head of one penny, and as long as you're very careful about it, the water will continue to bead up instead of falling off the penny. Those water molecules will continue to pull against each other and overcome the force of gravity pulling them downward. You'll also notice if you've ever tried to pour a liquid besides water, if you try to pour oil, for instance, it's totally different. You can pour water and stop pouring water without ever spilling any. It's much more difficult with oil because oil, among other things, don't have strong surface tension like water has. And so those water molecules, once they get going, are not as likely to grab onto each other and keep pulling. We overcome surface tension all the time using substances called surfactants. Surfactants is just anything that can break that surface tension. Soap is a very common surfactant. It's used to break the surface tension of water. If you tried that thing that I mentioned a minute ago with the paperclip in a bowl of water, once you get it floating, take just a couple drops of liquid soap and drop them somewhere in that bowl of water, and after a few moments that paperclip should sink, because the surfactant gets in there, it interferes with the hydrogen bonds between those water molecules, and it allows that surface tension to be broken. Another property of water caused by hydrogen bonding is water has very low vapor pressure, meaning that it does not evaporate very rapidly. Anytime a substance evaporates, whether it's water, alcohol, or whatever, you've got a container of it, and up there at the container, those liquid particles are in constant motion, and they're randomly moving and bumping into each other. Once in a while, they will collide in such a way to where one particle gets tossed up into the air, and if it has enough energy, then it will just stay up there and float off and become a gas. It will become a vapor. That's evaporation. Because water has got so much hydrogen bonding going on, the other water molecules that are in there prevent molecules that get knocked up in the air from escaping. They drag them back down, and therefore liquid water evaporates very, very slowly. By contrast, you take other liquids that have a high vapor pressure, things like rubbing alcohol, gasoline, the acetone in nail polish remover. All of those things have a high vapor pressure. They evaporate much more easily. All of those things also have in common a very strong smell, and they're all very flammable because all of those particles vaporize very easily. It's easy to combine them with oxygen and burn them. Water, on the other hand, it's very, very difficult to try and burn water. Another strange property of water: water has an unusually high boiling point. Boiling point, of course, is just the temperature where a substance changes from a liquid to a gas. Anytime you have boiling, you're applying heat energy to those molecules, and as they move faster and faster and faster, more of them are jumping up off the surface, and that's boiling. With water, again, because it's got so much hydrogen bonding, you have to add a lot of energy to break up those hydrogen bonds and get those particles to change from liquid to a gas. In this diagram, you see something called a phase diagram. It might be a little hard to see in the video, but what this shows is the three most common states that water will fill: solid, liquid, and gas. You see here that we've got temperature in degrees Celsius on the bottom axis and pressure in kilopascals on this axis here. Right at this point, we have 101.325 kilopascals of pressure. That is 1 atmosphere of pressure. That's the pressure that you or I would be under if we were standing at sea level on planet Earth. And if you see, as the temperature increases, when you reach this is 0 degrees Celsius, that's melting point. That's where water, under normal pressure, will go from a solid to a liquid. If you keep increasing the temperature, you get to 100 degrees Celsius, that's boiling point. That's where it will change from a liquid to a gas. Now you notice that that's only melting point and boiling point at this pressure. If you change the pressure, then you change the melting point and boiling point. If you increase the pressure, then water will actually remain a liquid at much colder and much warmer temperatures than it normally does. If you decrease the pressure, then you can actually cause water to become a gas at a lower temperature than 100 degrees Celsius. You can actually boil water at much less than normal boiling point. You can boil water without ever really getting it hot if you decrease the pressure that's sitting on top of it. Down here we have what's called triple point. At this point right here, it's 0.611 kilopascals of pressure and 0.01 degrees Celsius. At this point, if you could get water at this particular point under these conditions, you would see water existing in all three of the phases, solid, liquid, and gas, simultaneously in the same place. Another strange property of water is that water has a very high specific heat capacity. If you recall, specific heats or heat capacity both deal with the amount of energy that a substance can absorb or release without changing temperature, without increasing or decreasing its motion. Water, again, because of that hydrogen bonding, it's very, very stable, and so you can add quite a bit of energy to water without getting a lot of change in motion, or water can radiate a lot of energy without really cooling off. This is important, especially here on planet Earth, because so much of our planet is covered with liquid water. That water absorbs energy and releases energy, and that helps to regulate our global temperature. You may think that we have very cold winters or very hot summers, but really the little changes we go through here are very small compared with other planets in the solar system. Water, when it becomes a solid, also has some interesting behaviors. You can see in this diagram down here, here's liquid water, and you can see the dotted lines represent hydrogen bonds loosely holding those water molecules together. Water is very unique in that it is the only substance that I'm aware of anyway that is actually less dense when it's a solid than it is when it's a liquid. Most other substances, as they decrease in temperature and they start slowing down, the particles crowd in closer and closer together and they become much more dense. And as you all know, when something is more dense, it will sink as opposed to less dense things which float. Water, because of this hydrogen bonding, as it cools down past a certain point, it will actually become less dense as those hydrogen bonds serve to shape it into these little hexagonal shapes. Okay, those little ice crystals, which will then leave empty space in that crystal, which then allows solid water to be much less dense. This is why ice floats on water. Most other substances, if you do the same thing, their solid form would sink. This is a really nice thing. If you happen to be a fish and you're living someplace where the water freezes over in the wintertime, if the water freezes over up top, that means it keeps all of the heat in the water underneath from radiating out, so you don't freeze to death. If solid water did not float on top of liquid water, then you would have a bunch of dead frozen fish. Like most things, water does become more dense as it gets colder. It hits its densest point at 4 degrees Celsius. So once it hits 4 degrees Celsius, it stops becoming dense, and as the particles slow down more and more, the hydrogen bonds begin to move them into that little hexagon shape, and they begin to spread out and become less dense again. If you've ever seen a snowflake, any snowflake, if you look at it very, very closely, you'll see that it's just a hexagon or some kind of variation on a hexagon, and all of that comes back to that crystalline shape laid down by those molecules as they slow down and as they're pushed into that shape by those hydrogen bonds. And that brings us to the end of part 1. Thanks for watching.